Hello everyone. Today we're going to be looking at hydrogen NMR spectroscopy. NMR stands for nuclear magnetic resonance. We will be looking at how we can produce the spectra and how we can interpret them. So, what do we do? NMR is taking advantage of the fact that some atoms have an uneven number of nucleons. Nucleons are the protons and the neutrons in the nucleus. So hydrogen 1 only has one proton. So it's an uneven number. Carbon 13, which is an isotope of carbon, has an uneven number as well. So atoms that have an uneven number of nucleons generate their own small magnetic field. So you can consider them as tiny magnets. Now, these tiny magnets can align with an external magnetic field, which is this green arrow. Now, our tiny magnet, this red arrow, let's say it's hydrogen. The lowest energy state is if you apply a magnetic field, it aligns with the magnetic field. However, using radio waves, which is the lowest energy wave in our electromagnetic spectrum, we can cause it to flip, to align opposite to the magnetic field. This is a high energy state. Over time, it relaxes back to the low energy state. Okay, and we can detect this. This flipping to align opposite to the magnetic field is called resonance. Okay, let's see how this can be useful to us. So if we take the NMR of ethanol, we get a spectrum like this. Now, if we look here, I have included the molecule tetramethylsilane, which is our reference point in NMR. Okay, this is our 0 point. This is the magnetic field required to reach this resonance state, and we compare all other hydrogens to this one. Now, what is the scale at the bottom? The scale at the bottom is ppm, parts per million. Okay, so if it says 1 in the scale, it means you need 1/millionth the strength of the magnetic field less than tetramethylsilane. Now, why do we have this difference? Because if you have hydrogen by itself, it can align with the magnetic field and you can cause it to flip with a radio wave. However, the atoms it has around it, we say the environment around it, can affect the magnetic field required to reach this resonance state. Now, we don't see hydrogens in organic compounds by themselves. They're bonded, for example, to a carbon. And that influences how that hydrogen feels the magnetic field. Okay, because there is two electrons between the carbon and the hydrogen. Those electrons interfere with the magnetic field that the hydrogen experiences. Therefore, you may need a different magnetic field to what was required with a sole hydrogen by itself. Okay, now, depending on what element you have bonded to the hydrogen will affect how much magnetic field you have. If you're bonded to a CH, carbon is not that electronegative. It's more electronegative than hydrogen. So you will require a slightly weaker magnetic field than the CH3 bond, the CH bond in CH3 and tetramethylsilane, our reference. So you might need 1/millionth of the strength. So this peak here. However, if you have oxygen bonding to hydrogen, because oxygen is electronegative, it pulls the electrons towards it. So hydrogen is pretty free of electrons. So it experiences the magnetic field as if it was alone. Okay? And you need a much weaker field to achieve the resonance state. Okay, so you only need 2.5 millionths of the magnetic field required in a CH bond in the reference. Okay, please join part 2 for the continuation of this explanation.